Okay? Did you guys, anyone rewatch the videos to get Minitab going? All right. So we'll probably finish off this section of notes today and get started on the next section, the DOE 3. We're going to be real close to being finished today. So make sure to print off the DOE stuff for tomorrow, the DOE 3 stuff for tomorrow. This is where we left off. We did this group problem. And when we went through, we found those three effects were significant. The main effects of x1, main effect of x1, main effect of x3, and the interaction effect between those two variables. And then the last part of the problem, which was a very practical part of the problem, was now that you found these things are significant, that's not really that can't be the end of our study, because that's not going to tell someone what to do. So once you found these things are significant, then you have to use that information to figure out, well, these x1 and x3 seem to be doing something to our response, which was some sort of sealing strength. And we need to figure out, okay, well, what do we set these things at? What temperature are we going to run this thing at? How much polyethylene? Oops, that doesn't matter. And what's the sealing time? As far as polyethylene content, X2, it doesn't matter. So we still need to choose some value, and that's just going to come from somewhere else. We can lump that all into what's the cheapest way to do it. Okay? So there is an answer for X2. It just doesn't depend on our results. It's what's the cheapest, easiest, most repeatable way to do it, so forth. So x1 and x2, we have to figure out what's the temperature, how much time, or x1, x3. And it was a little bit awkward for us. x1 was pretty clear. And then we had a little bit of trouble trying to figure out what to set x3 at. The main effect seemed to be saying, no, set it at -1. The interaction said +1, given that x1 was at the +1 value. So we reasoned it through, but there should be a little bit better way to do this, especially when you have multiple interactions. Then it can be even trickier. So that, combined with other reasons, is let's take these results and say, let's go from, hey, we have 3 significant effects, to let's use that to build a model. And so a model means our response is some function of x's. So notice one thing, I put a little hat on this y, and that's going to indicate to us that that's our predicted values. So a y hat from here on out means that's a model prediction. A y without the hat means actual data. So we need to build a model. And a couple things. What are we going to put in our model? We're going to put in only significant terms. Right? So only the things that have proven themselves to be doing something are going to make it in the model. So our model would not have x2 in it, because x2 doesn't show up as significant in any of its terms. Does that make sense? So our model, in this case, is only going to have x1 and x3 in it. And the terms it's going to have a main effect term for x3, and then an interaction term for x1, x3. So let's look at building a model. And to do that, we need to think about what is an effect. So I've asked this several times. Who wants to do this in words? Explain the effect, the x1 effect in words, please. Who thinks they got it? Jeff. Right. Let's say that with specifics. Or, again, you said the temperature is higher. Let's be someone else sharpen that up with more precision, and we won't make Jeff do it again. That was good. Gets us started. John.
So would you say, like, as the seal temperature goes from
whatever. What is y in this problem? You got it. By 130? Yes. Yep, that's it. What is y? Read back in the problem. Say, is it some sort of strength? Strength of seals. Okay, so that is right then. So the X1 effect would be as we increase the seal temperature from 225 to 285, the seal strength increases by 130. Does that make sense? So if we're going to make this plot, if we're going to make a main effects plot for X1, so if we had y here, and we plotted X1 here, and we had the minus value and the plus value, we'd have a number there, and their difference between them is how much? How much did y change when X1 went from -1 to +1? 130. Right? And right now, the best we can do is just draw a line through there. We're looking at linear models. Okay, does that make sense? Okay, so now let's think about if we want to write this equation, if we want to model, let's just say, for instance, X1 was the only thing we're going to put in our model. I'm going to have a linear model. B naught is going to be the y-intercept. We can figure that out. B1. This is the equation of a line, right? And B1 represents the slope of that line. What is the slope of this line? Someone give me a number. 65. Rise over run. The run is 2. +1 minus -1 is 2. So the slope there is half the effect. And if we had X2 in the model, it would be half that effect. If we had an interaction, it would be half that effect as well. So we can put this model together, and what we're going to do is go from effects to coefficients. B3, and I'll call that B13. And the coefficients are simply half the effects. So that's pretty straightforward. We can take those and put those into our model. So that's what this is getting at now. So our model is going to have an intercept. And this ends up being the overall average, the mean of the data. Remember before when we kept putting this value in? That ends up being your intercept. If you think about your cube of where you took data, the average of all those is at this middle point, 0, 0, 0. You're in between -1 and +1. It's the center of the cube, and so that would be 0, 0, 0. That's going to be your intercept. So that's that average of all the data points. And then the coefficient in front of B1 is going to be half the effect. The coefficient for X2 is going to be half the X2 effect, and so forth. Even the interactions, it's half the interaction effect. So our full model in this case, our full model could be, if everything was significant, our full model would look like this. P2. We have the main effect terms plus the interaction terms. And even the three-way interaction term. So I got a little messy. Let me try to clear up some stuff. I'll stop. So it's thinking for a while. All right, so everyone remember, I'm sure everyone remembers, you've got that picture in your head, that full model that I just wrote down that you can't see anymore, right? And every term in there corresponds to some effect we calculate, and we get the effect over 2 or 1/2 the effect for each of those terms. So let me kill this. This is not going well. Okay. So we'll go back here. So now, if we think about the voltage example, that's where this is getting at. Let's look at another one, how we would get a model from data. So if we remember that voltage example, let's go back to it. Where was that? Here we go. Here's a voltage example. So when we looked at this, we found X1 was significant, right? And 2.306, and the X1, X3 interaction was significant. Those are the only two things. So our model is going to be the mean, which is this guy. So it's a B0 plus B1 X1 plus B13 X1 X3. So an important part of this is in our model, we're only going to have significant things. If there are factors that are just doing nothing, we're not going to put them in our model for a couple reasons. It just makes it messy. And the other part of it, it actually makes our predictions less precise if we try to use up a degree of freedom to model noise. So only things that are significant. Does everyone agree that the main effect of X1 and the interaction between X1 and X3 are the only two significant terms? Right? Okay, so then we have one exception that we do, and this is just sort of standard practice, that if, as in this case, if you have an interaction term, so that here X1 and X3, we will include the main effects of both variables that are in a significant interaction. So because X1 and X3 combine here or interact, that means we will have main effects for X1 and X3 in our model. That's why. So we would include the insignificant X3 main effect because it appears in this interaction effect. And not everyone does that, but that's the most common practice. And there's various sort of philosophical reasons for modeling that the main effects are like the trunk of the tree and the interactions are like the branches. So you got to have the main effects if you have the interaction effects. But we would include that only because of the significant X1, X3 interaction. That's the only exception to the statement of the model includes only significant terms. Okay, so if that's our model, we would say we have 668.6 is our mean. B1 is the effect divided by 2. B3, sorry, B1 is this one, minus 31.63. So that's B1, that's B3, and then the interaction term is the effect divided by 2 times x1, x3. Any questions of how we've got those coefficients? One thing that's really easy to do, I do it all the time, is it's easy to look and put the t-value in for the effect just because you read off the wrong row, so be careful with that. Again, it's very easy to do that. So this model then allows us to predict the voltage, in this case, at different settings of x1 and x3. x2 doesn't change anything. But just like all empirical models, don't extrapolate these. What do I mean by don't extrapolate? You're not going to use it to predict values outside your data. Good. So for x1, we have -1 and +1. We can predict values in between -1 and +1, but if you are trying to predict a value at x1 of 1.2, don't use this model to do it. So we got data over this range. Our model's good over this range. Once we get outside that range, we don't know what's going on. Lots of different things can be happening there, and so it's really important not to do that. Okay, any questions on the modeling part? Oh, that's a great question. How do we know it's a linear model? At this point, we're just assuming we have 2 points. We'll model it as a line. In the next set of notes, we're going to test that assumption and say, is it linear or not? It's a great question, really important. One of you guys back there, who thought?
I'm just curious, are there some positive or negative that help tell you whether to minimize or maximize it?
Yes, the sign, the positive or negative sign tells you exactly that. So, well, wait a second. You said if we're trying to minimize or maximize y? Yeah. Okay, so whether we minimize or maximize y depends on the experiment, right? If it's an amount of, say, impurity in our sample, we'll probably try to minimize it. If it's a strength, generally we try to maximize it. And then once we know from practical experience what we're trying to do with y, you know that during an experiment, is once you know whether you're trying to minimize or maximize, well, then this sign comes into play, right? So if you have a -1 in your x1, that's going to cancel with this -1. It's going to make y hat bigger, if that's what you want. Like in this case, it's not so clear. But if that's what you want, then good. And then a positive value, it makes y smaller. So you just have to think through, what do I want to do? Minimize or maximize y, and then the sign in front of your coefficient here is going to tell you if you want the high or low value of x1 and x2. Notice one thing, if we're looking for a maximum or a minimum in a linear model, it's got to happen at the endpoints, right? So if we're looking at a maximum, if we're trying to maximize or minimize y, these x1 and x3 or whatever values there have to be -1 or +1. Right? So if you have a line, if you're trying to maximize, this doesn't happen in the middle unless it's not a line. And we'll get to that later. Okay, so what I've asked to do in the notes is write your model for this situation. first thing you probably want to do is figure out what terms are in the model. And then you just need to find your coefficients. Got it already? Good. Okay. Questions? You guys got it? All right. Yeah.
Where's the constant?
What's that?
Constant again?
Constants are half the effects. That's the mean. Yep. It's the mean of all the data points, which we calculate in that first column of the spreadsheet. Okay. I think most people have this down. We looked at this and said, from before, our model's going to have the mean, which is this guy. And significant effects were, which ones? I recall x1, x2, x3, and x13. So we're going to have those terms in the model, right? So in numbers, the mean is 508. B1, 130 divided by 2 times x1 plus 172 over 2, so forth, minus 68. You guys get that model? Okay. So now you can plug in any value of x1, x2, x3 that's between -1 and +1 inclusive, and you can predict the seal strength of those wrappers. The great thing about, okay, so any questions on that? Now this model is in terms of coded values. So we're putting in -1s or +1s. So if you have a seal temperature of 225 degrees, you're not going to put 225 in this model, you're going to put in -1. You could do the math, it's not that hard to do, to convert these x1s, x2s, x3s into their real units. Temperature, time, and so forth. And the coefficients change, obviously, numerically, and then you could use that model. But I think it's better to leave your model in coded values simply because, well, a couple things. There's two reasons. One is then the coefficients are all on the same basis, right? So they're all coded high to low values. So you can compare the coefficients. This one has a bigger effect than that one. That's one reason. The other reason is that it serves as a great warning when you when you're extrapolating in your model. So here, you know, if you try to put in a coded value of 1.5, well, then you're extrapolating. With temperature, you have to remember what range of data you took it over. So that's sort of two arguments why generally we leave our models using the coded values. Yeah. The negative sign is just simply, well, if you put in +1 for x3, it's going to reduce your predicted y. So it functions just like you would expect it to in your algebra class. All right, questions on that? So now we can use this to figure out our settings for x1, x2, and x3. And if it gets complicated, you can just add a column in here of y hat and figure out your model predictions at all locations. It's a pretty easy thing to do in Excel, just to put in your model. So if you're ever in that situation, sometimes it gets complicated, and I can show you an example of that. Any questions so far? Getting a model. That's the goal. We're taking data, and this is what we want. We want a model. Once you have a mathematical model, you can do a lot of things with it. All right, so we just did that. I'm going to go through this example, then we'll do another group problem. I'll go through this one very quickly. They were looking at cracking in turbine blades, obviously something that you don't want to happen. And they did an experiment. They figured out, hey, these are the 4 factors in making of these blades that might contribute to cracking of the material. And we're trying to minimize the crack length. So they got together, and I don't know if the book gave the true values of these, but they set high and low values for each of those, and then ran an experiment and measured the crack length, and that's our y value. And how many replicates do we have? 2. How many total points do we have? How many total experiments? Good, 32 total runs. Okay, good. So we have 16 unique experiments, 2 replicates at each experimental condition. And this is the standard run order, but remember, in the real world, we would randomize these. It's just not indicated one way or the other there, but that's what you want to do. So this is the design table, right? These are the experiments we're going to run. For Excel, we need to flesh this out into the calculation table to get all the interactions, and that's what we have here. So let's just go through this. So we add a column to calculate the mean. We have the 4 main effects. We have the 2-way interactions, 3-way interactions, and 1 4-way interaction. And remember how to get this column, right? To get this number, we multiplied A and B together, and so forth. So I think you know how to get all the plus ones and minus ones. Then we have, here's our y value, 2 replicates. There's our average y from those 2 replicates, and then the variance. So if I know this and this, I can get the variance. How many degrees of freedom in that one? In that variance right there, how many degrees of freedom? 1. How many total degrees of freedom in the experiment? 16. Very good. Okay, this is another response. We'll talk about that later. Same with this. So now we can put our sum product in there, calculate our effects, calculate our t-values. This one, remember, we got that as it's 2-sided with 16 degrees of freedom. So that's our hurdle value. T is 2.12, and the bolded values are the ones that are significant. So a whole lot is significant in this experiment. So the main effects of all 4 factors are significant. We have 2 2-way interactions, and sadly, we have a 3-way interaction. So I say sadly because this is quite rare. So please make a note of that. Hesitate to even put this example in your notes because I don't want it to mislead you into thinking that three-way interactions aren't rare. They are rare. So, and when you get one, you are a bit suspect of your data. So keep that in mind. Three-way interaction is really rare. So we want to figure out, we've got these significant effects, and we want to figure out how do we minimize crack length. So to do that, we would want to build a model. So we'd have the mean plus the main effects, or we had A in there, right, instead of X1. And then the two-way interactions and the three-way interactions. And in this case, you can take that model, plug it in here, and that's what I did in this spreadsheet. So this would be our model prediction, and this is it's complicated enough, and you can say, oh, okay, there's what our model predict would be the minimum crack length. Actually, that one would be even smaller. And notice one thing, because of noise, your model can give you values that don't seem to make any sense. Right? A negative crack length doesn't make much sense, right? But again, there's noise in the data. Your model can do that. So that would be the condition that would minimize it, whatever that would be. We would say it would be approaching 0. So those would be good conditions to run it. So if I don't miss. So if we set A at its high value, B and D at their low value, C at the high value, that would give us the minimum crack length. Does that make sense? So I also did this in Minitab, and we can say, okay, here are the main effects plots for A, B, C, and D. They're all significant, but remember, let's think about this. Which of these four, A, B, C, D, would you explain each of these or not? So these are the main effects. Would you start writing text in your report to explain the main effect of A? Yes or no? I see a no. Why not? Right, there's a significant interaction that involves A. So even though we can make this plot and it's valid, it doesn't really communicate everything that's happening with A. So we wouldn't explain that main effect plot. Would you discuss this one for B? No. Why? Because of that? How about C? There's a significant main effect with C. Would we explain this main effect plot? No. But for D, we would say you could discuss the average effect of whatever D was, amount of grain refiner. Whoops, there we go. So you would discuss that one. A, B, and C, you wouldn't discuss the main effect plots. You would start looking at interaction plots. So A, B, and it was AC were the two-way interactions. So this is where you would start to explain what A, B, and C are doing. We're not going to talk much about that crazy three-way interaction because even that would make this suspect, but you're probably never going to have to deal with a three-way interaction in real life. Yeah, John.
Why again for ABC not look at the main effects, just the interaction?
Okay, good question. So why don't we explain these things? It's because there's so much more happening. So for example, here's the AC reaction, or AC interaction. And if I was going to explain the main effect of C, right? So based on this, I would say when A is at the -1 setting, C doesn't do much. Everyone see that? That slope line is almost flat. The effect of C is almost nil. But when I set E at its high value, then as we increase C, Y drops considerably. That tells you what C is doing. It's actually misleading to try to lump that all together into that. Does that make sense? Because it depends on what A is doing.
So how can you tell just by looking at the main effect plots?
Oh, good question. How can you tell by looking at the main effects plots? You can't. What you have to do is use this information. These were significant. So A, B, A, C. So A, B, and C, I'm not going to explain main effects plots. I'm going to go right to the interaction plots. It's a good question.
Because D wasn't included in those two, you can't discuss that.
Exactly. So what John's saying is the interaction effects with D are insignificant. So D does not show up in a significant interaction. So the main effect of D is not misleading. So this is a good way to discuss D. Is everyone clear on that? Okay. All right, let's do this group problem. That's to wrap up everything, most things that we did. I'm going to add another part. Another part of the problem that we'll add just for fun is for the residence time, when you're determining that main effects, write down that formal hypothesis testing. So to tie it back into this is exactly what we're doing when we're looking at our spreadsheet. We can't forget that part of it. This sort of question is very immutable to test you on exams. What I'm interested in is not can you kind of blindly crank out a spreadsheet knowing in this box I do this calculation, but actually know why you're doing a calculation, what it means, those kind of things. Make sure to work with people around you. See what they've got. Again, a tip, you might want to write down NF right away. Questions?
Just really hoping my calculator's calculating these variances right.
Just check it by hand one time, and then you'll be sure.
That's true. Well, but that's the over t value. There's a t value to the over. There's a t value.
Anybody stuck? Does have a question? Yeah.
How do you do the hypothesis test again?
So think about chapter 6, go through all the steps. So for this, you say the null hypothesis is the mean of this effect is 0, alternative it's not 0, and then just draw that, just go through all those steps. Yep. by now, parts A and B should be able to do that, and that should all make sense. If anything in parts A and B does not make sense at this point, you probably need to come in and start asking me questions and get all that straightened out, because that's the stuff we've gone over several times. You've done homework in it. You're going to do some more homework in it. So think to yourself if you can do A and B quickly and know what it means. All right. Well, it's about time to end class, sadly. Don't fret, though. We have tomorrow. There's always tomorrow for your statistical dreams to come true.